Hey Hayesfield, it is Ben here, and I'm going to run through my chemistry paper that I've just done. Short paper, 2 pages, on the time of flight mass spectrometer. And essentially, here, the first page I have talking about the actual apparatus. We have an analysis breakdown, similar to the one I had on the night after my Hayesfield interview, because I thought I absolutely bombed it. Turned out it didn't go so bad, and, well, you know what, we're here. So we have an analytical breakdown here, and on the second page we have an interpretation of the mass spectrum, which is normally presented on a graph, and it's essentially how you can plot the data and then how we can interpret the data from it, from this investigation. I also have a little Paint doc open here that I can go through the method with at the same time to make it easier. It helps me explain. So essentially, the mass spectrometer is a machine that we use to determine the mass and the abundance of isotopes in an element. And in the AQA spec, we use a time of flight mass spectrometer. So essentially, an isotope is an atom that there's multiple different types of the same atom that all have different number of neutrons. So we are calculating the mass of these isotopes and the abundance of them. So firstly, we will take a sample of our element and place it in the sample chamber. So the next thing we need to do is we need to ionize our isotopes and convert them all into positive ions. And the most common method I find to ionize these atoms is called MALDI, or matrix-assisted laser desorption ionization. But essentially, we're going to we'd have a little tank off to the side here. It's unfortunately in the diagram I have in the doc. We'd have our ionizing source right here, and that is going to ionize our sample. There we go, which is located in the sample chamber. Now that our samples are all ionized, they are all going to have the same charge, because essentially all isotopes of an element will react in the same way. So for instance, if one isotope has a charge of 1, all of the isotopes will also have a charge of 1. So these isotopes that are now positively charged ions are attracted to the negative plate located at the beginning of the drift chamber, which is this here, negative plate. And essentially, because we have positive ions and a negative plate, the positive ions are going to accelerate towards the negative plate, which is going to increase our kinetic energy, or the kinetic energy. It's going to increase the kinetic energy in our isotopes, or our ions. After they pass the plate, however, though, then all acceleration will stop, and they're going to move at a constant velocity from the start to the end of the drift chamber. It will only be a constant velocity if there is a closed system and there's no other particles in the drift chamber that the ions might collide with, which essentially, I'll go through how you do that in a minute. So due to the fact that all the particles will have the same charge as each other, because they're all ions of the same element, the resultant speed is purely going to be determined by the size of the element. So the velocity is going to be inversely proportional to the size of the particle. Essentially meaning a smaller particle is going to move much, much, much faster than a larger particle. And that's going to help us differentiate between isotopes. So once the ions pass through the negative plate, again, they stop accelerating. And because there's no external or internal forces that act upon the ion, they'll maintain a constant velocity. At the end of the drift chamber, we have a detector, which is essentially going to pick up when our positive ions touch the very end of the drift chamber. Now, when our ions make contact with the detector, an electron is transferred to them, which will create a flow of current. Which just seems a bit random. Why is that important? Well, essentially, the size of the produced current is measured by the machine, and we use that current to calculate the abundance of each isotope. And then we have also measured the time for our ion to move down the drift chamber. Sorry about that. The time for the ion to move down the drift chamber And essentially, the time is recorded by the machine, and then we use that time to calculate the mass. So the time will calculate the mass. The time from the ion to move from point A to point B is going to give us our mass, or it's going to be used by the machine to calculate the mass. And the charge, the size of the current that is produced by contact with the detector, is going to be measured by the machine, and we use that to calculate the abundance of our isotope. Now, where I mentioned earlier that we have a closed system in the drift chamber, this is achieved by using a vacuum. And we use a vacuum to make sure that there is no molecules in the air that can be collided with, to ensure that we have a fair test, essentially. So now we're going to move on to the mass spectrum interpretation. So we have our data presented in a graph so that this can show us how to plot the data in a graph and how to interpret it in the graph. And essentially, you're going to be able to see that there is a number of peaks here. And if you can count them, that's how we work out the number of main isotopes that an element has. So for instance, copper, we have 1, 2. So there are 2 main isotopes in the element copper. And it is presented as, the y-axis is presented as abundance of each isotope as a percentage of a whole. So our sample that we put in is going to be 100%, if you think about it like this, and all of the isotopes added together are going to equal 100%. And that's how you check that you have counted the number of isotopes correctly. Because 69.2% of our sample is isotope A here, and 30.8% is isotope B. If you add these two together, then you get to 100%, which is our whole sample. And on the x-axis of the graph, we have the M to Z ratio, which is essentially just the ratio of each ion to its charge. But it's always normally going to be a singular positive charge. So essentially you can kind of think of it as the mass number, or the relative atomic mass. Anyway, that is all from me. Hope that was useful. In the description I will leave a view and edit access of both of these pages, and also a copy of the rough notes I made for the paper. I'll also enclose those to an email to my chemistry teacher. So yeah. Anyway, I hope this was useful. And yeah, have a great one.